In this video, I'm going to show you a much quicker method to solve indeterminate beam problems. And I'll use this example taken from the internet. On YouTube, there's a structure-free channel. And this example, which I'll provide a link for, talks about the slope deflection method. And it's a series of 3 videos. Altogether, it takes about 30 minutes to solve the problem up to the bending moments. And it is a indeterminate beam, a continuous beam with 2 fixed supports and a roller support. So let's take a look at how that problem can be solved in a straightforward manner. So I'm going to use my CAS calculator to help, and I have written a program that has an additional function called INUN that can integrate delta functions and step functions, which I'll use to model my loads. So perhaps first let's look at the formulation of my approach. I would call my approach the Swiss approach, just an abbreviation, which I'll discuss soon. So here's the original problem, and I will instead take 5 steps to solve the same problem, but I'm going to get more. I will actually go up to the deflection of the beam, y of x. And here are the assumed reactions, the force at A, at B, and at C, and a moment at A and at C in those assumed directions. So my so-called Swiss approach is as follows. First, I am going to write down 2 static equations. So it's quite obvious from this picture. You've got the sum of these upward forces, A, B, and C, should be equal to all the downward forces. So there's a 10 coming down, so I write it as a negative quantity, and 1 kilonewton per meter for 20 meters. So that's altogether 20 units coming down of force. And also a moment equation, which I will assume positive counterclockwise. So the assumed MA contributes in a positive way. And then we have a moment arm of 5 units for this force that comes down. So it causes a clockwise moment to be registered as a negative quantity, plus this reaction B coming up. So that gives you a anti-clockwise moment. So that's a positive quantity with a moment arm of 10 units times unknown force B assumed upward. And then we pretend this UDL is all concentrated with a magnitude of 20 kilonewtons and a moment arm of 10 plus 10. So that's 20 meters. And it's clockwise, so it's a negative, plus 30 is the moment arm, times C, the reaction assumed upward. And finally, we have a clockwise, hence negative term, MC, the reactive moment at the fixed end at C. All right. So it's very straightforward. Once I have obtained all the static equations, I just go ahead without solving for the unknowns, because I don't have enough equations to solve for them. I will just go ahead and write down my load, W of X. That's the next step. I'm going to model each concentrated load as a delta function. So there are 2 of them, this one and this one. And by convention, anything coming down is positive. So I've got 10 kilonewtons coming down, multiplied to a delta function that acts at 5 meters. So it's argument is x minus 5. And this is an upward reaction, so I include as a negative term happening at 10 units or 10 meters. And then I have this UDL that starts at 10 meters, so it's 1 unit or 1 kilonewton per meter times a step function that gets turned on at 10 meters. And that's all for my load. And then I can go ahead and apply the usual static knowledge. I know that in order to get my shear force, I need to integrate minus W and add the initial term, which is A in this case. We can take a look at that. So if you consider an infinitesimal piece of beam here, you already have a outward reaction A, and V naught, the starting value of the shear, is whatever it needs to is needed to balance that outward force. It is defined as downward positive, so it has to be exactly equal to A, the reaction. All right, so with that in mind, we know the initial value of V being A, and then we also know the initial value of the bending moment. If you allow me to erase something first. So what about the initial moments? Well, it is also assumed to be positive if it makes the beam smile. So that's my m at x equals 0. And it is just whatever is needed to balance this assumed anticlockwise m sub a. So they have to act opposite to each other. So we know that has to be equal to minus m sub a. So that gives me also the initial value of the bending moment, right? So we are going to do integration. You integrate minus W, you get V. You integrate again, you get M. Of course, each time adding the initial values of those. If you integrate further, then we know since EI y double prime equals M, then we know that if you integrate M once, you get EI y prime plus a constant whose physical meaning is EI y prime at 0. But we know in this case, it's a fixed end at A, so it's 0. You integrate one more time plus a constant, you're going to get EIY. And the constant again is 0 because its physical meaning is EIY at 0. Okay, so that completes the third step. And then once I have the expression for y of x, which will carry those unknown reaction with me, I am going to substitute some x values at those extra supports that I see in this problem, namely at x equals 10 and 30. 10 is where the roller is, and 30 is where the extra fixed end is. So evaluating y prime or y or both at those places, I'm going to get my extra equations. Namely, I know that at the roller, y has to be 0. And at C, the fixed end, both y prime and y will be 0. So I get 3 extra equations together with my 2 static equations. I now have 5 equations. I'm going to solve all of them for all my unknowns, which are the 3 forces and the 2 reactive moments. Okay, so let me just go ahead and do exactly that on my calculator. So here's my calculator. I've opened my program, which allows me to integrate step functions and delta functions. So what's the first step? S in Swiss, the abbreviation. So actually, I'm going to start my stopwatch and see how long it takes to solve this problem. So I'm going to just copy my static equations over. So E1, equation number 1 will say that A plus B plus C, my unknowns, minus 30. Total downward force is 0. And E2, my second equation, says that MA minus 5 times 10, which is 50, plus 10 times B minus 400 plus 30 times C minus MC equals 0. So I've got two equations. I'm not going to bother solving for the unknowns. I don't have enough equations at this point. So now I input my loading, W, colon equal to 10 times a delta function. So you find the delta symbol by pressing Control and this book key. You find the delta symbol, and it's 10 units happening at 5 meters. So that's how we write it as a delta function, minus the unknown B times another delta function. So let me do that again. And this time it's happening at 10 meters, okay, plus 1, which I'm going to skip. It's a kilonewton per meter, times a step function that gets turned on at 10 meters. So that's it for my loading. The rest is just mechanical integration, which I will do all in one line. So V is going to be its initial value, which is A, plus the integration of minus W. Notice that because W contains these special functions that this calculator doesn't know how to integrate, I have put in an in-house program for their integration through this function called INUN, integration of unit step functions. Actually, why don't I just show you the result? Okay, so it will involve some step functions again. But this time, let me do it all in one line. M is going to be its initial term, which is minus MA, plus the integration of V, and I use the colon sign to get an extra line of input or extra input in one line. Next, what I'm going to do is integrate this M, okay, and get my EI times Y prime, which I'll call it EIYP. So that is just the integration of M. And then I'm going to finish my integration by doing one more, okay. EI times Y, the deflection curve, is going to be obtained by integration of EIY prime. In both cases, in both these two integrals, there's the constant of integration is 0 by physical arguments that I discussed earlier. So now, since I'm done with the integration, I can go ahead and evaluate some extra boundary conditions. For example, I know that 0 is the value of EIY when it's at the point B. Okay, let me just show you. Okay, at B, it's x equals 10. So this is how you do it. Okay, EIY is an expression, the above expression. You can substitute by pressing Control equal and use this vertical bar for substitution. X equals 10. All right. So that's an equation that says 0 equals blah, blah, blah. And let me call that my third equation, E3. So you see there are some step functions, nothing to worry about for now. Okay, later on we'll get rid of these things, which should be 1. Step function for positive argument is 1. But let me just go ahead and finish building my extra equations. The fourth equation is going to say that there's a 0 slope at the right-hand end. So 0 equals EI y prime at x equals 30. And finally, my fifth equation says 0 equals EIY at x equals 30. That's the zero deflection condition at the right-hand fixed support. Okay, so we see there are some obvious ones, which I will now simplify by defining the step function now. Okay, I did not define that earlier because I need h to be symbolic in order for my integration program to work. But now I don't need to integrate anymore. So I'm going to define my step function explicitly using the internal when function. When x is smaller than 0, then return a 0. Otherwise, give me a 1 when the step function has a positive argument. Okay. Now you can take a look at E3 again. You see that those step functions are gone. Okay. Or simplified, because now it knows, for example, h of 5 is 1. So now what? Now we can solve by using the solve command, E1 and E2 and E3 and E4, and finally E5 for all the unknowns, A, B, C, MA, MC. All right, so here are the solutions. I could have stored them into something called SOL. So here are the values for those reactions. Now I'm going to do a substitution, okay? Because if I look at my M, the bending moment expression, I have, you see the reaction values. So let me substitute the known solutions to those reactions into M. So let me call that M plot for plotting purposes. It will be M with the solution substituted. So you see everything is numerical now. It's ready for plot. But let me clean it up a bit more. M plot will be itself times some trimming functions to get rid of the negative x regions plot. Okay, because I know there's no beam there, so there's nothing to plot. So I do it like this: h of x minus h of x minus 30, so that there will be a 0 in here if you're on the left-hand side or the right-hand side of respectively A or C. Okay, so that's my M plot. Oops, typo. M plot will be itself times some trimming. Oops, sorry, I have to fix this. Okay, so this is something you can plot. We can go ahead and insert a new graph and plot. Now you can do a zoom fit, for example. Also, you know the region where you want to see this plot. We don't need too much negative values for x, but it is a 30-meter long beam, so let's make it go to 35. X scale 5. Okay, just zoom out a bit. And now we're ready to get the max and mean values. You can use menu, analyze graph max to catch this maximum value and also the minimum value. Let's get this one and also the final one. And let's compare it to the results obtained in the video or the original author's results of this problem. So we can see they're identical. Okay, minus 26.4. Here he has minus 26.386, which is the same thing. Okay, we can adjust the, okay, we can store into a variable, for example. So into say M1, whatever. Okay, and go back and check its value. What is M1? Okay, so I have solved the same problem but let's not forget that I also obtained the deflection curve as well as the slope of this beam as a function of x. So I believe I have done more in much less time. I have spent about 10 minutes so far, but it took the slope deflection method about 30 minutes because that's his third video in his series. So I think my direct integration approach should be more efficient than applying slope deflection method to solve this sort of problems. And in fact, I get more. Actually, why don't I just finish getting all the maxima? Here's another one. So you can see my answers are identical to his, but only a fraction of the time is needed. So that's the end of this video, and thank you for watching.